Today's topic is AC Thevenin and max power. And recall that the same physical laws that govern voltages and currents in a DC circuit apply to AC circuits as well. Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, law of conservation of energy. So practically speaking, what this means is that if we transform our AC circuit sources into phasors and our resistors, inductors, and capacitors into impedances, then all our tricks to solve circuits will apply. So recall that a Thevenin equivalent circuit replaces the network, shown here in the cloud, with a single voltage source, shown here, and we call that my E Thevenin or V Thevenin, my Thevenin voltage, and a single impedance, shown here, and we call that Z Thevenin, Z Thevenin. So for a Thevenin equivalent circuit, recall that we follow the same three steps in the process. The first one is to remove the load, so it's an open circuit, and measure the resulting voltage. That would be from here to here, and we call this V Thevenin. The second step would be to determine the Z Thevenin, my impedance. And so again, I'm going to remove, as I've removed the load in the open circuit, I'm going to zeroize or kill the source. Shown here, it was a voltage source, so I'm going to put a short there. And I measure my Thevenin from the perspective of the load that I just removed. So this would be called Z Thevenin. And I'm going to find that. Each step, I'm going to go ahead and redraw the circuit. And then finally, I'm just going to redraw the circuit, and here it is. Here's my voltage source, E Thevenin, my Thevenin impedance, and then I reconnect my load impedance that I just removed. Okay, so here are my steps, 1, 2, and 3. Now, for max power transfer, I say that Z load, or we say that Z load would equal Z Thevenin complex conjugate. So we find Z Thevenin, take the complex conjugate of that value, and that is the load that we have to deliver the maximum power. Now, what we'll find is that the complex conjugate ensures that the current is in phase with the Thevenin voltage, and the load resistance is delivering max power. So let's see what this does to our max power equation. But first, a review of complex numbers. Suppose I have a complex number C, and I'll put an arrow on top to indicate that it has magnitude and direction. It's a vector. And in the rectangular coordinates, I have A plus JB. In the polar notation, I have the magnitude of that vector, C, with an angle of theta. If I were to draw this on the complex plane, my real axis is the x-axis and my imaginary axis is on the y side. I see that A in the real direction and B in the y direction, or the imaginary side, the vector that's drawn is C from the origin. The complex conjugate of that value, C, or that vector C, is C with an asterisk in the upper right corner of the vector. And what that means is that I'm going to take the opposite of the complex number C. So in this case, it's A minus JB, and in the polar notation, it's the magnitude of C, which is the same, but the angle is a negative angle, indicating that the angle is going in the opposite direction with respect to the positive real axis. So in this case, C is going down in this direction in the fourth quadrant, where C complex conjugate is right there, A minus JB. And when I add the two vectors together, C plus the complex conjugate of C, that would equal A plus JB plus A minus JB, where the imaginary parts will cancel. And this would leave me with 2 times A. So in the application of max power transfer in AC circuits, notice again that I redrew right here my Thevenin circuit, where my Thevenin voltage is here and my Thevenin impedance is shown on the top, Z Thevenin. Now we say that the Z load is equal to Z Thevenin complex conjugate, means that max power is transferred to this load right here, and I'll just put it in red again. Okay. Now, let's see what happens to the current when I find that through that path. Well, we know that in a circuit like this, we have two impedances, Z Thevenin and Z load, and I'm going to add those two together because they're in series. And so now I have, for my current equation, E Thevenin, which is my voltage, divided by Z Thevenin plus Z load. They're in series. Now, if Z Thevenin and Z load are complex conjugates of each other, notice what happens to my reactance, the imaginary part. Well, that actually goes and cancels each other out, and I'm left with a real value for the current, or that I'm looking at E Thevenin divided by 2 times R Thevenin. It's not a real value, but it's in phase with the voltage. Okay, so if I were to find the current through that path, as I've done here, I can find the power now as I squared R load. And if you follow the logic here, you can see that my max power transfer equation, E Thevenin squared divided by 4R Thevenin, is the same for an AC circuit as it is for a DC circuit. Now, keep in mind that E Thevenin is a vector. Okay, it has magnitude and phase, so I might call this, I don't know, magnitude C with an angle theta. So the magnitude of that E Thevenin vector is simply just C. So this is a scalar. So when I go to use the equation now, I'm just using the scalar value for, or the magnitude of that vector, square it and divide it by 4R theta, 4 times R theta, and that gives me real power, which is a real number. It's not a complex number. It's just real. Okay, and that's max power transfer. So let's do an example and seeing how this works. I have a network of impedances, and I also have a voltage source of 100 volts with an angle of 0. I'll call this Vn. And I'm just going to go around the horn here and label all my impedances. Z1, I'll call this one Z2, I'll call this one right here is Z3, this one Z4, and I also have a load impedance, Z load. Okay, I also noticed that the frequency of the input right here is equal to 191.15 hertz. Okay, so what does this mean? Well, now what I'm going to do, before I even solve the Thevenin circuit, I need to define my impedances. So notice that my units for each one of my impedances can either be millihenries or microfarads, so I have to convert those into impedances. So in this case, I'm going to go look at Z1. Z1 is purely inductive, so there's going to be zero resistance, zero real resistance, and it's going to be a positive because it's an inductor. I'm going to put my J here, and I'm going to multiply it by omega L. And that's equal to 0 plus J times 2 pi F, where frequency is 191.15 hertz, times 100 times 10 to the minus 3. That's 100 millihenries. And that's equal to 0 plus J 120.1 ohms. Okay. Z2 come on now. Oops, it's stuck. There we go. Z2 is equal to, well, that's a 50 ohm resistor, so it's purely resistive. There it is. And it has 0 in its imaginary part, so that one's easy. Okay. Z3, that's purely capacitive, so there's 0 real part to that impedance. And I'm going to put a minus there because it's a capacitor, J times 1 over omega C, which is equal to 0 minus J times 1 over 2 pi F times 20 times 10 to the minus 6. And that's how much, that's the value of that capacitance of 20 microfarads. And that equals 0 minus J 41.63 ohms. Z4 is equal to, well, again, that's another capacitor. So I know I'm going to have 0 resistance, and it's purely capacitive. So I have a negative sign, and I have a J 1 over omega C. And in this case, it's 1 over 2 pi F times 10 times 10 to the minus 6, which is equal to 0 minus J 83.26. So that makes sense because it's twice Z3. Okay. Step 1 in my process, now that I have all my impedances labeled, step 1 of the process tells me to remove the Z load, redraw, and solve for V Thevenin. All right, so let's go ahead and redraw that circuit. Here's my circuit. V in, and I'll call that, yep, here's my V in. Here's my initial, here's my Z1 impedance. Oops. Here's my Z2 impedance. Coming down this way is going to be my Z3 impedance. And I also have Z4. Okay, now I've removed my Z load, and what I'm going to do is find the voltage across the terminals where I just cut from A to B. And that's called my V Thevenin. And V Thevenin, if we see that there's no current that's flowing through this path here or through this path here, that really all I have is current that flows in this path through those 3 impedances there. So in this case, what I can see is that it's simply an application to voltage divider rule to find V Thevenin, which then would equal Z3 divided by Z1 plus Z2 plus Z3. Notice how I put the arrows on top because they're vectors, times V in. If I do that math, plugging in all those values for my impedances, I don't know why I have an extra Z there, then the value of V Thevenin is equal to 44.74 with an angle of minus 147.5 degrees volts. So here's my Thevenin voltage. That's step 1. Step 1 is done. All right, let's do step 2. Step 2 is, I'll just give myself some more room. Step 2 is to solve for Z Thevenin. And remember, we need to kill the source or sources to do it. So I'm going to redraw my circuit, and I'll come back to where my source is. So I'm going to redraw my circuit. Here's Z1. Dropping down here is Z2. Dropping across here. Whoops, I forgot oops, I labeled this wrong. This is Z3. This is Z2. And this is Z4 here. Now, for a voltage source, when I kill it, what that means is that I'm dialing it down to 0, and therefore it's a short circuit, shown right here. That's my short circuit where my voltage source used to be. And notice here that I have my two terminals, and I'm going to, from that perspective, I'm going to find Thevenin. Thevenin, in this case, is equal to, well, if I just follow my path from A to B, I can go through Z4, and I'm going to see that I have a series connection of Z1 and Z2 going this way, and in parallel with that I have Z3, and they all come back to B. So Thevenin then would equal Z1 plus Z2. I'm going to go from the far end and work my way back to Thevenin. And that expression, those two in series, are going to be in parallel with my Z3. And together, that expression, when added to Z4, yields Thevenin. And when I do that math, Thevenin is equal to 140.95 with an angle of minus 85.93 ohms. That's my Thevenin. Okay, step 3 is to just redraw my Thevenin. Thevenin equivalent circuit. Okay, so let's do that. Let's redraw. Here's my Thevenin voltage. We'll call this V Thevenin. And we have my Thevenin impedance, Z Thevenin. And it's connected now. Back to it is my load impedance, Z load, from the very beginning of the problem. Let me show you that. That's this guy right here. Okay, so now I've gone ahead and plugged it back in. And I want to know what my max power is delivered to that load. Well, Z load would then equal Z Thevenin complex conjugate. So Z load, I'll just write it down here, Z load is equal to 140.95 with an angle of plus 85.93 ohms. Okay, so there we have my circuit, and there's my Z load, my Z Thevenin, V Thevenin. And what I want to know is, I want to determine the Z load that will allow maximum power to be delivered to the load. And this is the answer right here, Z load. Complex conjugate of Z Thevenin. The next thing I want to find is the max power delivered. Okay, so part B is to actually find or calculate max power. Okay, I know that in that condition Z load is equal to Z Thevenin, complex conjugate, and my equation then applies where P load is equal to V Thevenin max or the absolute value of that Thevenin voltage, because it's a vector, divided by 4 times R Thevenin. All right, so what are those values? Well, we see that my voltage is shown in the first step, 44.74 volts. 44.74 volts. 44.74 squared divided by 4 times R Thevenin. Now, R Thevenin is the real part of my load, or the Thevenin here, and this is written in polar coordinates. And what I'm going to find is that when I put this into into rectangular coordinates, z Thevenin, the real part is, I'll say this, that I'll say it down here. The real part of z Thevenin is 10 ohms. And so it's going to be 4 times 10 in the denominator. And now P load then is equal to 50 watts. And that's my answer.